let's start the MacDub lecture. So last time we tried to solve this Schrödinger equations for harmonic oscillator problem, and we use this brute force way. Namely, we simply directly solve the Schrödinger equations. And we use some smart, educated guess to guess that this solution u of y, this eigenfunction, is given by this polynomial in y called h function, multiplied by this e to the minus y squared over 2, where this exponential decay factor comes from the solutions when y goes to infinity, or y. Let me show you the y. Okay, y is x times this some prefactor. Okay, so when y goes to 0, and this solution is given by the h function. Okay, so and last time we proposed that the h function could be in general a polynomial in y to infinite number of terms. The y's m's power, where m can actually go from 0 to infinity, and we plug in this ansatz h function back to the Schrödinger equation, and we find so-called recursive relation between the coefficient am and am plus 2, like this. So, and we immediately find that these coefficients could be classified in terms of even odd terms, and even terms shows this even number of powers in y with a prefactor a0, a2, and a4, and odd terms contains odd power in y, and coefficients are a1, a3, and a4, and these even odd coefficients are decoupled, they are independent, and this reflects the fact that we have the parity symmetry, this mirror symmetry of this potential, harmonic oscillator potential, with respect to this vertical axis. And today we further pursue this direction. We try to find out this coefficient am and try to again solve everything, including the eigenfunctions and the eigenenergies. To do so, let's just look at this again simple limit where m is very large, limit when this m is very large, where this y polynomial is actually shows a very large power here. And in this limit, we could simplify this recursive relation, because this m plus 1 and plus 2 can be approximated by this m times m, which is m squared. And this, when m goes to almost infinity, this epsilon is actually a finite value, and it doesn't matter. And 1 is simply 0, okay, compared to m. So then we could just simplify this recursive relation to this form, where am plus 2 is approximately given by 2 over m times am. So this approximated form helps us to further derive all these prefactors. So we can imagine that when the power in y is large enough, and we could use this approximated form to express this coefficient am. Okay, and as a result of this h function, we could consider this as a sum of two parts. The first part is the polynomial in y, whereas the power in y is actually small. Okay, when m is small, and also plus the terms when m is large. So when m is small, it's just a finite value, so we simply just don't pay attention at this point. Okay, so we only pay attention to the terms when m is large, because this term actually determines this long distance behavior of this eigenfunction. Okay, and we just plug in this approximated form when m is large, and we collect all the terms when m is large enough. And suppose when m is n, and this capital N is a very large value, and then we start to collect the terms starting from capital N. Capital N plus 1, capital N plus 2, capital N plus 3, and so on and so forth. Okay, so then we keep analyzing this large n term Okay, suppose we just look at the even solution. Of course, you could also study solution, but it's the same. And so for even solution, we just plug in this capital N, an even number, which is 2 times the integer k. And in such case, you could further simplify this even solution when n is even, and you plug in this relation, capital N is 2k, and you get this polynomial in terms of y to the power of function of k in exponents, and you simply just look at this patterns or some of the regulations between the neighboring terms. Okay, so you could realize that this term is actually go to the infinite number of order in y polynomial, and we could rewrite this infinite number of terms because this, although this n is large, but still this is finite. But then since this hy polynomial, we assume in the beginning, has infinite number of terms. So we can go from capital N, that term, up to always to the infinity. N goes to infinity. And if capital N is 2k, then you could plug in this kind of a coefficient inside the bracket where this power goes from, say, 2k to infinity, right? And then you could look at this regulation and patterns of these coefficients and the power exponent in y for different terms, and then you could realize that this is nothing but exponential of y squared subtracted by a finite number of terms. Okay, so if you Taylor expand this e to the y squared and you subtract this by the finite number of terms in the bracket, and you can show that this is the same as the previous term. So this is exactly the term here. Okay, so why do we need to do so? Well, you will see the importance of this exponential function right here. Okay, so let's just plug in this form back to the h of y, and h of y is something like polynomial in y at small powers plus a constant times y squared, where y squared is here, and times exponential of y squared. Of course, you need to subtract this by the finite number of polynomial in y, but this is also hidden here. So all the finite number of terms in polynomial in y are summarizing in this term. We don't pay too much attention about this because they are just finite values. So we worry about this long distance behavior, because if you plug in this long distance behavior and y is large, and this exponential function times this y squared back to this complete eigenfunction u of y, and you will find that, remember, when y goes to infinity, we found that this exponential decay function right here, but then there's exponential increase function in h of y right here. So these two will cancel to some extent, but they're not completely cancel out, because this is e to the y squared, but this is e to the minus y squared over 2. Okay, so you take the multiplication of these two exponential factors, you still get y squared times e to the plus y squared over 2. So this term is troublesome because when y goes to infinity, this is exponentially large. So this goes to infinity, and we know that this is not correct, because as we know already that when y goes to infinity, you get almost infinite height barrier or walls, so that any wave function should vanish right at the boundary when this potential goes to infinity. So the u of y should be 0. So that's what we expected. But what we got is infinity. So something is wrong. But what is wrong here? Well, the thing that go wrong is that we assume that this h of y is a polynomial with infinite number of terms. Okay, because exponential function is really could be regarded in the Taylor expansion sense the infinite number of terms. Okay, polynomial in y. So we should expect that this polynomial should stop, okay? And h of y should be a polynomial in y with only finite number of terms. So we don't expect that this is going to continue indefinitely. So we need to truncate. We need to stop the polynomial somewhere. But how to stop this polynomial? Of course, the only way that we can make this term 0 and all the coefficients become 0 after this term is when these coefficients are 0. Remember, both even and odd, we have this relation. So this am coefficient is related to the am plus 2. Okay. So if for some large value m, this some coefficient vanishes, for example, this am plus 2 vanishes, we could demand that this bracket here, which is just some variable, some constant, 2m minus epsilon plus 1, and this could be 0. Okay, if we demand that this is 0, then m plus 2 is actually 0. Okay, so if m plus 2 is 0, then am plus 4 should be 0. Am plus 6 should be 0, because you can use the recursive relation to actually derive all the coefficients beyond that term. So when this coefficient becomes 0, initially, then all the coefficients associated with the higher powers in y should also vanish. Okay? So let me just illustrate this. For example, if a2 is actually 0. So if a2 is 0, then a4 is what? Some number divided by another number times a2, right? As a result, since a2 is 0, a4 is also 0. And likewise, a6 is also 0 because a6 is a function of a4 times some constant prefactor. Okay? And a4 is 0, so a6 is also 0. So once you get the first 0 in the coefficient, and all the following coefficients must be 0 because of this recursive relation. Okay, so we need to truncate this h polynomial somewhere when n is large. And the only way that we can truncate this expansion is by demanding that this bracket vanishes, because in general m is integer, m plus 1 is integer, m plus 2 is also integer, and am plus 2 is something unknown, and am is also finite value. The only way that we can make this 0 is by demanding that this bracket vanishes. And this condition is precisely the condition we get this quantized energy level like this. And if you demand that this 2m minus epsilon plus 1 is 0, then this translates into this physical quantity. Is capital E is the eigenvalue. It's given by h bar omega times n plus 1/2, where n is the term when this bracket vanishes. As I mentioned, when this happens, this am plus 2 is 0, so an plus 4 is also 0 all the way to a infinity. So then this polynomial is just stopped right at m equals to n. Right? Okay. And this eigenenergy E is a function of n, where n is an integer number, ranges from 0, 1, 2, up to infinity. And these are precisely eigenenergies. So eigenenergies, if you plot it here inside this potential well, and you will see that this is the energy level for the ground state, and this is the first excited state and the second excited state. So the ground state energy is 1/2 h bar omega, the first excited state is 3/2 and 5/2 and so on and so forth. So the energy levels are equally spaced. So the energy spacing between adjacent energy levels is precisely h bar omega. It's uniformly distributed energy levels, and there's some most important properties of this quantized energy levels in harmonic oscillator problem is this E0. So this is probably the second time that we see this, that the ground state energy is not a zero energy state, because omega is a positive value, right? H bar is a finite value. H bar over omega, H bar omega over 2 is non-zero. It's positive value. So in other words, the ground state energy has a positive energy. The ground state is not a zero energy state, but a positive energy state. And such phenomena is called quantum zero-point energy. And this is a very important concept, or quantum zero-point motion, saying that in many quantum mechanical problems, the ground state of the quantum system is not a zero energy state, it is a positive energy state. And what is that positive energy that we are talking about? Remember, in this infinite potential wave problem, we have the same conclusion that the ground state energy has a finite kinetic energy. Remember that. Okay? The average value of the momentum vanishes, but the average of their kinetic energy is not. And the zero energy in the ground state corresponds to the finite amount of kinetic energy when you compute this expression value of a p squared over 2m at ground state. So meaning the particle is still moving back and forth inside the well, even if it's in the ground state. Okay? Is that just on average, the momentum of this ground state particle just cancel out. But all the time, the particle is in motion. The particle never stops. Okay? It's just that when you measure the momentum, it vanishes. It's not because the particle is at rest. It's just because they have an equal probability to get the positive velocity, negative velocity, and that positive and negative velocity get exactly canceled. But if you measure this kinetic energy of the particle, of course, it is positive value. So the particle is actually symmetrically moving back and forth inside the well, inside the potential, oscillator potential. And this kinetic energy is actually the finite ground state energy that you see here. Okay, so we will come back to this later, but this is the way that we could quantize the energy levels of a harmonic oscillator problem. So we haven't finished everything yet, because this is only half of the problem solved, where we find this eigenenergy, but we haven't found this eigenfunction, because the odd coefficients am needs to be calculated as well. So let's take a short break. When we come back, let's just finish the job by calculating all these coefficients am. Any questions so far? So these are just some algebras and some arguments. So it's not difficult to understand those arguments. But later we will introduce another much better way to derive this eigenfunction, eigenenergy of a harmonic oscillator problem, which is from this operator method. Okay, so we will introduce this maybe today. Okay, so let's continue. So we truncate this h of y polynomial up to m equals to n, and we try to analyze all these finite terms before we reach this truncation term, right? Where we denote this, the general term, the smaller in y polynomial by k, where this k is the term that before we reach the truncation. So in general, when m equals to k, and you could use this recursive relation between a of k and a of k plus 2, and by plugging this, all this previous, derive the recursive relation, and this is given by this red box. And so this allows us to really derive all these coefficients one by one, starting from the term right before the truncation. Okay, so suppose the truncation term is a n, and therefore a n plus 2 is 0, but you could use this recursive relation to derive all the terms. Okay, for even parity terms, this A2k coefficient could be derived by this recursive relations as the product of all these coefficients, say from A2k minus 2 to A2k minus 4 and so on and so forth, and up to all the way to the very last prefactor, and finally you get A0. Okay, so you actually go backwards from the term that survives, the final term that survives, and you could actually use the recursive relation to go backwards to find this coefficient. In general, for these odd parity solutions, the coefficient can also be derived in a similar way. So, but you know that for even parity terms and even all these odd coefficients must vanish, right? And then all these even powers must be truncated as some finite power in y. And so it's for n odd, all these even coefficients are 0, and all these odd coefficients are finite before the truncation term. So let's just take a very simple example of this finite n if this truncation term is that when little n is 1, and in that case the A3 is actually 0, but A1 is non-zero. Okay? But all this even power term must be 0 because n is odd. So A0 is 0, A2 is 0, and so on and so forth. And in this simple case, n equals 0 case, you only have this one coefficient, which is finite, which is A1. Great. So, and we started from here, and we could simply just write down all these coefficients if we simply just know A0 or A1 from the beginning. But at the end, we'll show that this actual function is a very famous special function in mathematical physics. It's called Hermite polynomial. So the Hermite polynomial is the solution of this differential equation, which is second order differential equation. Again, you could plug in this polynomial, actual y polynomial, back to this Hermite equation, and you'll find that this is precisely this h of y. And so you can get this recursive relation that comes from this Hermite equation, Hermite polynomial equations, and this looks pretty much similar to that we found of h of y function. Anyway, so this is just a more mathematical way to derive this h of y function. So in general, this hn of y corresponds to those terms. So you can see that even though this Hermite polynomial is a function of exponential function times the nth derivative of this exponential function e to the minus y squared, but at the end, so this exponential, two exponential factor may cancel out, so and you get finite number of terms. Okay, and there's a normalization condition for this Hermite polynomial. Okay, so but in any case, you don't need to memorize all this Hermite polynomial, but you just need to know that this is precisely this h of y function that we try to solve. And you could compare this a coefficients, an or a2k or a2k plus 1. You compare this coefficient with the coefficient in front of the Hermite polynomial. So this little n in the subscript of the Hermite polynomial refers to the exact same value in this h of y polynomial, which indicates that this polynomial has n terms. So h3 of y is what? This, and so on and so forth. Okay, so then we are done, because this Hermite polynomial is simply just h of y polynomial that we try to find. And these coefficients really give you this a coefficients in h of y polynomial. So let the final task is to check this orthogonal normalization condition. And we have these normalization conditions right here for this Hermite polynomial. So let's check this orthogonal between two different eigenfunctions, say u1 and un. So let's just go back to this Schrödinger equation. Suppose we know this eigen energy of u1 and un, and we also find this Hermite polynomial for this u1 and un. So now we like to check whether these two eigenfunctions are really orthogonal with each other. And to check this orthogonality of these two different eigenstates of the Hamiltonian, we need to show that this is 0. The overlap between this u1 star and the un wave function or eigenfunction is 0. Okay, so you could check this by some kind of a mathematical manipulation of this Schrödinger equation, and we integrated the Schrödinger equations on both sides of these two equations, and we find the boundary value of this integral, and the boundary value must be 0 because of this square integrable conditions of any Schrödinger wave function. And at the end of the day, we will find that this is given by this condition right here. So let me just, maybe I can just write it here. So if I make this combinations of these two equations like this, and from the Schrödinger equation, I get this on the other side of the equation, E1 minus En, U1 star Un. Okay, so if I subtract these two equations from the Schrödinger equations, and I get this on the right-hand side, and then I integrate over the equation on both sides. Okay, so on the left-hand side of the equation, on the top of the equation, we get the total derivative of something, right? And you integrate over the total derivative. So this integration and this derivative that's canceled, you get the boundary value, right? So this, the first term gives you the boundary value. But from the boundary condition, that's both u and u star, or du dx, should vanish right at the boundary, okay, plus minus infinity. So the first term vanishes. But let's look at the bottom line here. So this right-hand side of the equation, which is the overlap integral that I just mentioned between u1 star and un, integrated over the x, and multiply some prefactor. Okay. So, but on the top, we find this is 0, but on the bottom line, since E1 is not the same as En because there are two different eigenstates, so the eigenenergy should be different. So these factor E1 minus En should be finite, and this 2n over h bar square is also finite prefactor. So these factors cannot be 0. The only way that this term is 0 is the overlap integral is 0. Okay, so by this kind of a calculation, and we can show that for different eigenstates, the eigenfunction should be orthogonal. So meaning it looks like if you take this vector as an analogy, so these two vectors are orthogonal to each other. So if you calculate the inner product between these two vectors, so v1 vector dotted v2, if they are orthogonal, and you should get 0. So the analogous way to define this inner product between two vectors in quantum mechanics is this overlap integral, which we will define more properly next chapter. So now we have everything. So we have the quantized energy levels for harmonic oscillator, and we find the eigenfunction, which is nothing but this Hermite polynomial, okay, multiplied by e to the minus y over y squared over 2, and as a total eigenfunction. So we have eigenenergy and eigenfunction, and we are done. So the just final part is the I draw some pictures of this even R solutions of harmonic oscillator eigenstates. For example, the even parity states, we have this U0 and U2 and U4. For odd parity solution, we have this U1, U3, and U5, which is odd parity in X. Okay, so this is U3 and this is U5. So you can look at your textbook and see these plots of these eigenstates, eigenfunctions. Okay, so this is the end of the chapter 4. So we will take a break and we will start a new chapter, which is the operator method in quantum mechanics, or general structures of wave mechanics, which we already discussed to some extent. Okay, so let's take a short break. So far, any questions? Yeah.
那个步骤可以再讲一次。
哪个部分？这里。
中间开始。
这里。Okay. So what's your question?
就是有听没有懂。
The Hermite polynomial is the same as h function. So this is the statement here. The Hermite polynomial is a solution of this differential equation right here. We solve the differential equation for Hermite polynomial, and it gives you precisely its h function, h of y, that we proposed earlier. This is a statement. Is that clear? Okay, so let me just repeat. The capital H with n subscript as function y is precisely this little h as function y. The capital H and the y satisfy this differential equation. When you solve this differential equation, you find that this polynomial is precisely the little h. Now, okay? And we don't have time to tell you how to solve this Hermite polynomial. This is the scope of your applied maths or mathematical physics. But let me just, your textbook just tells you that this is the equation if you use the polynomial method to solve this Hermite polynomial. And this is the thing that you will find, this relation between all these different Hermite polynomial. Okay? So they all come from this differential equation. That's all. Okay? And the final solution of this Hermite polynomial is this one. Okay, so analytically you could solve the Hermite polynomial, and this is given by this function of y. So there are two exponential functions. One is e to the y squared, another is the nth derivative of the e to the minus y squared. Okay, so if you take the nth order derivative of the e to the minus y squared and multiply by e to the y squared and times minus 1 to the power of n, and you get to this hn of y that I just mentioned over there. For example, if n is 1, so little n is 1, and so you take the first derivative of the e to the minus y squared with respect to y, you get what? Minus y squared, right? Or if n is 0, okay, if n is 0, then you don't take any differentiation, right? If little n is 0, you simply just forget about this derivative, multiply e to the y squared times e to the minus y squared. These two canceled, and n equals 0 minus 1 power of 0 is 1, right? So you get what? 1. This is precisely what you get. If little n is 1, and you need to take the first derivative of this thing, which is what? You know that, right? d e to the minus y squared dy, you tell me. And when you down this and you multiply this by e to the y squared, and you get 2y, which is this. When the little n is 3, you perform such a calculation, you find this is 4y squared minus 2, and so on and so forth. And this 1, 2y, 4y squared minus 2 is precisely this little h of y, which is a0 plus a1y plus a2y squared, and so on and so forth. If you simply just fixed a number of n, say h2, and you find that this is nothing but, if you simply just solve this little h of y and find this even solutions, right? So for even solution, a0 and a2, right? So a0 is minus 2 and a2 is 4, and all the other coefficients are gone. So your little h of y, if you expand this polynomial, will fit this Hermite polynomial. Is that clear? Okay, good. Okay, so let's take a short break. So after the break, we will start a new chapter, which is chapter 5. So by now you are able to do all this homework problem for chapter 4, right? So we mentioned part of the chapter 5 already in the earlier lectures. So I will not repeat what we have discussed. For example, the Hamiltonian operator and the expansion theorem, and the eigenstate of the momentum operator and Hamiltonian operator, and interpretation of the expansion coefficients, and so on. Okay, so I will start from section 5.3, which is the vector spaces and operators, because this is the starting point of quantum mechanics using this vector analysis and linear algebra. But before I introduce this vector analysis, so let me just remind you a point that I already mentioned in the lecture, which is the difference between the arbitrary wave function and the eigenfunction. Okay, so some of you may find this is confusion. This causes some confusion for some of you. Okay, so let me just, or relation, arbitrary wave function and the eigenfunction. So the best way to plan this is, again, if we go back to this expansion theorem that looks like the Fourier decomposition that we already discussed to some extent. So we mentioned previously that any wave function in quantum mechanics could be decomposed in terms of a complete set of eigenstates, right? Okay, so maybe we will repeat this one more time right here. So, for example, if you have just two states, two eigenstates from this potential well problem, for example. So I can label this as U1 and U2. Okay? And this expansion theorem tells us that you can form arbitrary wave functions based on the linear combinations of these two eigenstates or eigenfunctions. So we can form arbitrary wave function, which I call this psi, by simply just linearly superimpose all this U1 and U2 like this. So what is the physical meaning of this psi and U1 and U2? So maybe I already mentioned this in the past, but I will repeat that argument explanations right here, so that from now on, there shouldn't be any confusion between these two type of wave functions. So the eigenfunctions are the wave functions that satisfy the Schrödinger equation for certain Hamiltonian, and these are the specific eigenstates that the quantum particle in that Hamiltonian can live. Okay? In other words, if you take the measurement of your quantum particles inside this well, where this well supports only two eigenstates, and if you take the measurement say, measurement number 1, and I would like to measure which stage that the particle occupies. Well, then I use some measurement technique, and finally I get a conclusion that this particle stays at U1. Okay. Likewise, I could make a second measurement, and I find that this particle is at U2. Okay? But I can imagine that a general type of quantum particle inside as well, or before you take a measurement, could be either in eigenstate 1 or eigenstate 2, or you could imagine that I have some finite probability of finding the particle when this particle is at U1, and another probability where this particle is measured is found to be at U2. Okay, so such kind of a generalized linear combinations of the two eigenstates is called arbitrary wave function. Okay, so you can form any arbitrary quantum states based on this linear combinations of all these eigenstates in a particular problem. So different problem give you different normalized complete set of eigenstates. So for different problems, you could form such a linear combinations of all possible eigenstates, and you could construct any arbitrary wave function. Right? Okay. But for this arbitrary wave function, okay, it doesn't mean that this particle described by the psi could live in both states. No. This particle described by psi could be found in the state U1 or state U2 with the associated probability alpha squared and beta squared. Okay, so you take the 100 measurements. Okay, so you may find that out of the 100 times measurements, 40 times that the particle is stayed at U1, and another 60 times that the particle is found to be at U2. Okay, so you know that this particle, this arbitrary quantum state, has 40% of probability to be found at, say, U1, and 60% of probability to be found at U2. But this particle cannot be simultaneously at U1, U2 when you take the measurement. Okay, so when you take the measurement, this particle can live only in one of these n possible eigenstates. So the eigenstates is the states that when you take the measurement, the particle can take. Okay, the particle can be in just one state out of this n possible state. But you can imagine that I can construct a linear combination of all possible eigenstates, so that each of the measurement you may find the particles that live at different states. All right? Okay. So the eigenstate is the characteristic specific states that the quantum particle could live. But for arbitrary quantum states, you can imagine that this particle could have certain percentage or certain probability to be found in the particular eigenstates. Okay? So you can always construct such an arbitrary state. So this links to the so-called Schrödinger-Cat paradox. So if you know this famous story, Schrödinger joke about the quantum mechanics by saying that we have a basket, a box, and you put the cat here, but inside the box there's some machine where if the button is actually pushed, then some poisonous chemical material actually leak into the box, and so that when the cat actually breathes this poisonous air, and it will die. But there's a 50% of probability that the button would not be on. Okay, so this kind of a probability is that there's a 50% probability that this is on. When this button is on, the cat dies, but the button is not turned on, the cat can live. Okay, so if this dead or alive states of the cat can be represented by the quantum state 0, 1, so you could consider that before you open up the box, this cat, of course the cat is a macroscopic object. We cannot use the quantum state to describe the cat. So this is precisely this joke is about. Okay, so we can only describe the quantum state of the atoms, molecules, electrons, but never describe the macroscopic object like human beings, a table, and things like that. Okay, so suppose we can describe the cat in quantum state. The cat could be in the linear combinations of 0 and 1. And in this 50-50 percentage of the dead and alive, and this alpha is actually 1 over square root of 2, and beta is 1 over square root of 2. So before you open up the box, the cat, in principle, have the 50% of being dead, found dead, and the 50% of percentage to be found alive, right? And as a result, if you don't know the answer, if you do not open up the box where cat stays, then it is a linear combination of a dead and alive states of the cat, right? So this is what I call the arbitrary quantum state. Of course, we can design a different partition of this probability, 40%, 60%, whatever percentage you like. So you can construct arbitrary combinations of alive and dead states of the cat before you open up the box. But the tricky thing is when you exactly open up the box and this Poisson machinery may be triggered or may not be triggered, which you don't know. But once you open the box, then you actually take the measurement. Okay, when you take the measurement, the cat can be either dead or alive. It cannot be both dead and alive when you take the measurement. As a result, this correspondence is this. So 0 and 1 or dead and alive for the cats represent the eigenstates of your problem or your Hamiltonian. You have only 2 eigenstates. When you take the measurement, the cat can be either 0 state or state 1, can be either dead or alive. Okay? But before you open up the box, the cat could be in general dead or alive. And the states that before you take the measurement is precisely what I call this arbitrary quantum state. But when you really open up the box, you really take the measurement. You want to see whether the cat is alive or dead. And when that happens, you actually force the cat to be either in state 0 or state 1. There's no ambiguity after you take the measurement. But before you take the measurement, the cat could be in a linear combinations of all possibilities. It is only describing the possibilities that arbitrary quantum states refers to. Understandable? Okay? So before you take the measurement, and you could construct any arbitrary quantum states, which is a linear combinations of all these eigenstates. And when you take the measurement, the quantum particle can state only in one of the n possible eigenstates. But each measurement, you may find different answer. So that's the nature of quantum mechanics. There is some uncertainty here. Okay? And what we trying to do is to solve the Schrödinger equation and find out what is the eigenstates, and when we construct this arbitrary wave functions, we could actually expand based on this complete set of eigenstates. And we can design an arbitrary wave functions with the proper combination of all these different probability coefficients. Okay? And experimentally, we can design such arbitrary states. For example, you could design a states. So this will be your homework problem, right? So you could define initial states to be, say, like this triangle shape. Okay, so this is one of the examples of the arbitrary states that you can imagine. But then you could decompose this triangle states in terms of all the linear combinations of all these different eigenstates, Un. Of course, you could design, especially that this particle stay in one of those eigenstates initially, but that's fine. If the particle stays in one of the eigenstates, it will stay there forever, right? But if the initial state is not one of the eigenstates, each time you take the measurement, you may find that the particle is at different eigenstates. The eigenstate that says that once the particle stays there, it stays there forever. So that's the reason why we call this eigenstates, because it goes back to itself. Remember, if you solve the Schrödinger equation, the meaning of the Schrödinger equation, if you find that psi is given is one of the eigenstates, is that if psi initially is that U1 eigenstates, then if you apply this kind of operation, Hamiltonian acting on the U1, you always end up this U1 state with eigenenergy E1. If you measure this initial state to be U1 a million times, you get a million times that the particle is still at U1. So once the particle stays in one of particular eigenstates, it doesn't change. It doesn't evolve in time. It doesn't depend on anything. Okay? But if your initial state is not one of these eigenstates, for example, the triangle state, and you will find that it can be decomposed in terms of different eigenstates combination, right, with different coefficients. And when you take the measurement, you may find that each time this particle may stay in the same eigenstate or may not be staying in the same eigenstate that you find previously. So by now you should be able to distinguish between arbitrary wave function and eigenstate, eigenfunction of a particular Hamiltonian. And also the connection between the measurement, the quantum mechanical measurement, before you measure and after you measure. Okay, so these concepts are really go side by side. So you need to really understand what I mean by eigenstate. What is the measurement? And what's the quantum state of the particle before I measure? Or what is the state of the quantum particle after I take the measurement? Okay, so you need to think about this simultaneously. When you look at this wave function, I should ask myself, what is this wave function telling me? Okay, is it the eigenstate or is it the arbitrary state? Is it before to take the measurement or after take the measurement? Okay, if I take the measurement on this psi, would it stay always the same state or not? This kind of questions that you need to ask all the time when you really look at these equations and wave functions. Okay? So do not confuse between these two different concepts. As I mentioned earlier in the very beginning, that we could perform the Fourier transformation between the real space wave function and the momentum space wave function, phi of p, psi of x. And this kind of Fourier transformation, or kind of a spectral representation, is precisely this kind of a expansion that I'm talking about. Okay, so you can consider this p as some kind of eigenstate of a momentum operator, right? Okay, and u of p is the eigenfunction of a momentum operator, right? So this is nothing but this un that I wrote here, and phi of p is nothing but cn. Okay, so I can ask myself, if I have this arbitrary wave function in real space, and what is the probability that I find this particle to be in a momentum eigenstate un? And the probability amplitude is phi of p. And the probability is phi p squared. All right? And you could actually show that this kind of linear combinations of all possible eigenstates is precisely what the Fourier transform is telling you. Okay, so this is connected to this kind of a Fourier theorem. And remember, when you study applied mass, any arbitrary function of x could be expanded in terms of what? Sine and cosine, right? Oscillatory function. And the sine and cosine function play the same role as the eigenfunction right here. remember that. To remember any arbitrary function is a Fourier decomposition, something like that. Right? Right, okay. So anyway, so this is a remark that I would like to add since I received some questions from you. And I think many of you already learned this, but in case some of you are confused by these concepts, and these are really important. So maybe I will not skip this first few sections of the chapter 5. So any questions so far? Do you have a better understanding of quantum mechanics right now? So you should always think about the measurement. Okay, so the key word of today's lecture is measurement, measurement, and measurement. Okay, so measurement really links all these different concepts, wave function and eigenstates. Okay, so let's just start chapter 5, a general structure of wave mechanics. Great, so let me probably just start from the beginning. So we have this time-dependent Schrödinger equation, and the Hamiltonian operator is the sum of the kinetic energy operator and the potential operator. And we know that the kinetic energy operator is given by this p squared divided by 2n, where p is the momentum operator, which is the minus h bar d by dx, which will be acting onto any arbitrary wave function. So these arbitrary wave functions, if you want to solve this eigenstates of this problem, you must solve this Schrödinger equations. Okay, and in general, this could be, if this is one of the eigenstate, it should be like this. Okay, so if this arbitrary wave function psi of x satisfies the Schrödinger equation, and this arbitrary wave function must be one of the eigenstate, right? And this E is the general eigenstates that's in this problem, so E could be any eigenstate. Okay, but this is E1 and E2 and so on. So in general, you must solve this time-independent Schrödinger equation like this. And the little u E as a function of x refers to the eigenfunction of a particular eigenstates labeled by the eigenenergy capital E. Is it clear? The little u E is the eigenfunction of a particular eigenstate with an eigenenergy capital E. And so we are trying to solve this Schrödinger equation to find out that for arbitrary wave functions, what are the possible eigenfunctions that psi could live, right? Psi could live in any of these eigenstates, but what are they? Okay. Okay, so this is the other question that we tried to solve in the previous chapters. So capital E is our eigenvalue, which is the eigenenergies of this particular problem, and UE of x is the eigenfunction, which is the wave function that satisfies the Schrödinger equation. But of course, UE of x we have many u of E of x, so I need to label all these different eigenstates by this En here. So UEn refers to the nth eigenstates, but n could run from 1 to up to infinity, for example. The shorthand notation is that we remove this little n here, and we simply just describe the general eigenstates with eigenenergy E and eigenfunction UE of x. Is that clear? 100% clear what we are doing? Good. So suppose we already found such an eigenstate and eigenenergy, and we can show that those eigenfunctions are orthogonal, as I just proved a moment ago. Meaning, if we take the overlap integral that I just mentioned, UE1 starts and UE2 for any E1 and E2 states. Okay, and I find that this should vanish. I mean, all these problems should actually obey such a orthogonal condition for different eigenstates. So for different eigenstates, the eigenfunctions if you take this integral between this UE1 star times UE2 and integrate over from all the space with freedom, you find that this is 0. So provided that E1 is not the same as E2, which means that there's no degeneracy. So suppose these two states are really two states. Okay, so in some cases you have two degenerate states, meaning the two different eigenstates have the same energy. So yellow state is not the same as the red state, but they have the same energy. In such case, we call this degeneracy, or degenerate states. So we are not talking about degenerate states. For non-degenerate states, for separate two different states, if you take the overlap integral, you will see that this must vanish. Okay, so let's take a short break. When we come back, I will summarize all the other important properties of this structures of a wave function that Schrödinger equations are telling us. Any questions? 有什么问题吗？有什么不明白的地方吗？大家现在是不是都真的明白这些符号代表的物理的意义了？是吗？好，那这是非常重要的一件事情哈，就是我们需要很清楚的知道我们到底在做什么事情，然后这个对应到的物理，尤其是实验，到底是这个测量到底是怎么回事哈？所以量子力学的重点之一就是测量的概念跟我们的物理量有密切的关系哈。等于说我们还没有测之前，它可以处于很多不同的可能的本征态，但是我们一旦测量之后，它就必须是在其中一个本征态被我们找到。OK， 这个概念蛮重要的，还有统计跟几率的概念，还有测不准原理的概念啊，这些都是量子力学最重要的概念。好，那这些呢就落实在我们这个计算里面就会出现。好。之前我的课有一个一开始的第一章的作业，就是请大家 Google 什么是薛定谔的猫的故事，然后用你能够理解的方式来说明它的物理意义是什么。那我已经都告诉你们了，所以就不把它当作是作业了。Okay. But the story of Schrödinger's cat is really famous and well known, so you should really understand what is going on. And think about that if you are convinced by the Schrödinger. Okay, so we discussed the orthogonal properties of different eigenstates, and so let's just normalize this. So this is called orthonormal condition for this eigenstates, and which says that if you take the overlap integral between this eigenstate m and eigenstate n, and you integrate over the entire space, and you find that this is just a Kronecker delta function, delta mn, where this delta function gives you 1 if m is the same as n. If not, this is 0. So we just talked about when m is not the same as n, so this is orthogonal condition. But normalization condition is the first one, when m is the same as n, so you take the square, u star and u end, you take the square of the, because u star u is the same as u absolute value square, right? And this is 1. Okay, so you can check this normalization and orthogonal conditions for all these previous non-examples in textbooks or lecture notes, and you'll find that this is always obeyed. So based on the orthonormal conditions of this eigenstates, we could form a complete set of bases. This is precisely this expansion theorem is telling us. So any arbitrary wave functions could be expanded in terms of such linear combinations of these eigenstates. For discrete eigenvalues or eigenenergies, you could form a discrete sum. For continuous variables, you can actually take the integral. Right? Okay, so this is the thing that I just mentioned. Okay, so this un, when n goes to 0, 1, 2, up to probably infinity, and all such U functions, a collection of all such eigenfunctions. It's called complete set of bases, or sometimes we call this eigenbasis, because this is the basis functions that we can form any linear combinations of these eigenfunctions, and it turns into any arbitrary wave functions. Okay, so it's like unit vectors in the linear algebra. So we will make such analogies just a moment. So you can consider this as a vector analysis. Suppose I have two unit vectors in two-dimensional space, and each of this vector represents the eigenfunctions u1 and u2, and I could make any linear combinations of u1 and u2, and I could have any arbitrary vector psi, which is alpha u1 plus beta u2, something like this. And in linear algebra or vector analysis, we call this orthogonal unit vectors as a basis vectors. Remember that. Okay, so in three-dimensional space, we have x, y, and z, three different unit vectors. In other words, we can form any arbitrary three-dimensional vector based on the linear combinations of all the three unit vectors, right? And this complete set of eigenbases is something similar to this unit vectors in the vector analysis. So you can consider this, say, x unit vector as, say, u1, and y is actually u2, and z is u3. So like in the vector analysis that you could form this x, y, z unit directions by the three unit vectors, likewise, you could also form a basis vector in this eigenbasis u1, u2, and u3. And for three-dimensional space, this unit vectors x, y, and z are all the basis vectors we need. In other words, this is a complete set of basis vector we need to form any arbitrary three-dimensional vector is the three vectors x, y, and z unit vectors. Likewise, if a certain quantum mechanical problem gives you three eigenstates, and these three eigenfunctions form a complete set of eigenbases. So any arbitrary wave function in this particular problem could be formed by this linear superposition of the three eigenfunctions. And in this vector analogy, this is precisely what it means. Okay, so this complete set of eigenbases are formed by the collection of all eigenfunctions, and you can form any arbitrary wave function based on the linear combination of all these different eigenfunctions. Okay, so the job that we need to do is to find this un by solving the Schrödinger equation. Once we find this and we solve the problem, we know the probability distribution if you form any arbitrary wave function. And we know this probability, and we know the measurement results, we know everything. Great. So let's just look at the time dependence of this psi. So using this expansion theory, we could write down this called a Fourier decomposition or eigenbasis expansion of any arbitrary wave function in space and time. So you can consider this as a linear combination of all eigenstates, but including the time evolution, each eigenstate will evolve in time in a different rate, right? So remember this un xt is actually un of x. Time evolution factor is time evolution factor is e to the minus I eigenenergy t divided by h bar. So for different eigenstates, this energy is different. So the period of frequency of this kind of time evolution for different eigenstates is different. Okay? And this is the reason why we have this quantum oscillation for this ammonium molecule that we introduced earlier. Remember, for different eigenstates, this oscillation frequency are different. So is that clear? Everything clear? Good. So let's just talk about this again. eigenfunctions of momentum operator, just to refresh your memory. So we already solved this. Let me just briefly refresh your memory. So to solve this eigenstates of momentum operator, we need to solve this eigenvalue equation, right? So momentum operator acting on this eigenstate of momentum operator is given by this momentum eigenvalue times this eigenfunction, up. And this p operator is given by this partial derivative form, and this leads to what? The famous plane wave like solution. And you can check that this satisfies this orthonormal condition. Since this momentum variable is continuous, so the continuous version of the orthonormal condition is not the Kronecker delta function, but the Dirac delta function. So I defined Dirac delta function already. Remember, this is an infinitely sharp but infinitely narrow peak, right? For delta x, it actually goes to infinity if x goes to 0. But the integral over this entire space of a Dirac delta function is normalized to 1. So we can show that by plugging this momentum operator eigenfunction right here, and from this Fourier decomposition theorem, you can show that this is precisely this Dirac delta function. Okay, I suppose this is the end of the review of all this wave mechanics. So let's take a short break. After the break, I will briefly introduce these vector spaces and these operations, which we have not discussed. So we actually spent almost 2 months, 1.5 months, so to actually to arrive here. But this is the beginning of quantum mechanics. So this is the real beginning of quantum mechanics. So the previous chapters are considered as a review of your modern physics and plus some of the quantum mechanical interpretation, but the real mechanics part of the quantum mechanics starts from chapter 5. Okay, so from now on, the discussions will be based on this linear algebra and so-called Hilbert space, which is a vector space, but in infinite dimensional vector space. Okay, so as I mentioned, we have analogy between the vectors and the quantum states, right? So now we will formally introduce this analogy between the vector spaces and operators. So as we already defined that we could define the complete set of eigenfunctions, and this complete set of eigenfunctions play the same role as a set of a complete set of unit vectors in the vector space. So this is the first analogy telling us that you could expand this arbitrary wave function in terms of the complete set of eigenfunctions, right? So this is analogous to the construction of arbitrary vectors based on the linear combinations of the unit vectors. And you can sum up these two different Schrödinger wave functions, psi 1, psi 2, and the summation of these two different wave functions play the same role if we sum up two vectors in vector space. But of course, the actual algebras are different, right? So the vectors, we have this really, geometric shape of this orientation of these two different vectors and the angle between them. But there is no angle, but these psi's are complex functions, right? It has real and imaginary part. So in this real and imaginary part of this complex Schrödinger function, in that sense, you could have the similar effect as this summation of these two different vectors, because you can consider this projection and inner product of these two vectors, v1, v2, and you can also calculate corresponding overlap integral. So this is precisely what we mean. So this overlap between two wave functions is defined by this overlap integral. And this overlap integral in the vector analogy is simply just v1 dot v2. So you calculate this inner product between these two vectors v1, v2. In quantum mechanics, this kind of a inner product is defined as this overlap integral. Okay, so when the overlap integral vanishes, they have no overlap. Okay, so there's two separated wave functions that distribute at different spatial locations, and they don't have any overlap. So this overlap integral vanishes. So likewise, if you have this two vectors which are perpendicular to each other, there's no projection, right? So this v1 dot v2, when these two vectors are orthogonal, this vanishes, right? So you have no projection. No projection. So the projection is analogous to the overlap. So if you have any projections, meaning is v1 overlap with v2, right? You can project this v1 onto v2, right? So that these two vectors actually have an overlap. Okay? So, but if you have, in quantum mechanical problem, you have two wave functions. If they overlap, and you calculate this overlap integral, and this is finite. So in this sense, we take this interpretation that this overlap integral between the two quantum mechanical wave functions plays a similar role as the inner product, or we take the projection of this one vector and we project this vector onto the other vector. So we find the overlap between these two vectors, and quantum mechanically this overlap is defined by this integral. Okay, so that's enough for today. So next Thursday we'll have another 2-hour makeup lectures. So I encourage you to come. Okay, so prepare your midterm and submit your homework in time. Okay, I'll see you next Monday.